In the last video, we talked about these concepts of what is a high-dimensional data set, what makes data high-dimensional, as well as how do we define distances and similarities in these high-dimensional spaces. Now, before we get to truly nonlinear dimensionality reduction, I thought I would do just a short reminder of what linear dimensionality reduction is. So for example, if your data is actually on a plane, is actually flat, right? Then how do I find what this plane is, assuming that the data is embedded in, this plane is embedded in some higher dimensional space? Now, linear dimensionality reduction is the most popular, by far the most popular ways of doing it are a combination of techniques that are known as PCA, principal component analysis, and also singular value decomposition, the SVD. Now, there are lots of other videos that are available as resources, and I recommend that you go to those videos for a much more in-depth view of PCA and SVD in all its glorious detail, all the different ways they're related and how they're different and how do you use them. They're wonderful properties. I think the SVD is obviously the best matrix decomposition. I mean, this is obvious to anyone. But here, what I'm going to do is do a really short intro of PCA and SVD so that we can relate linear dimensionality reduction with similarity matrices and distance matrices before we then walk forward and take those concepts to nonlinear dimensionality reduction. Okay, so in the last video, we talked about this idea of high-dimensional data sets. And the data sets we started with are of this form where they are rectangular. So I have my X matrix, which is my data matrix, and it is tabular in the sense that it has n, which is the number of samples. In the previous video, we talked about this in the context of people. So each row is a person, and then each column is m, which is a measurement. So here's all the things that we might want to measure about the person, how tall they are, their shoe size, the number of siblings they have, and so on and so forth. And so my X matrix ends up being a m by m data matrix here, okay? So the whole point is that we want to use techniques to reduce the m dimensions that I would have used to describe this data set to something that's smaller than m. Now, m could be barely smaller than m, or m could be quite a bit smaller than m. M could start out being like hundreds and hundreds and thousands and millions of things, and I can reduce it down to like 2 if I wanted to, right? This may not be a good idea always, I'll talk about that later, but this is something that I can attempt to do, or at least do the best job that I possibly can. And so the PCA and SVD is essentially one of the best ways of doing this, assuming you didn't want to do anything fancy by warping your space. If all you wanted to do is assume that your data is actually flat, and I just want to learn the space. I want to learn the plane, the vector space that allows me to describe the data as long as it is flat. So I talked about this notion of Euclidean distances and similarities in the previous video, and I hinted at this fact that this dot product and this cosine similarity is one way of defining similarity. And so that's the connection I want to draw on here with respect to PCA and SVD, because succinctly what I'm going to do is define covariance, okay, the covariance of the data as the similarity. So I'm just going to assume that the similarity between measurements is, in fact, equivalent to their covariance. Now, I recommend that you go back to the statistics and probability videos in order to review what covariance is in all its glorious detail, in case that's something that you need a little refresher on. But I'm gonna go ahead and tell you that the covariance of the measurements of my data matrix over there can be computed as X transpose times X. So this is just like a really compact matrix notation for how to compute the covariance matrix of my data set, with the note assuming that this is already mean subtracted, okay? So this formula works if and only if you already mean subtracted your data set. In this case, it basically means that you're going to take the mean value of every single measurement and subtract that number from every column. Okay, so the mean height of all people is not 0. Whatever it is in your data set of all the people you collected, you take that number, maybe it's 150 centimeters or whatever it is, and you do all of the heights minus 150, so that the data set starts out, before you go into this covariance matrix formula, having means in every column of being 0. Whatever you got to do to get it to be 0, do that. That's what mean subtraction means. And then you apply this very compact matrix formulation to compute the covariance matrix. Okay? Now, the covariance matrix has some really interesting properties. I'm just going to tell you some of them. One of them is that if you work out the dimensions of the matrices, you'll see that the covariance matrix is an m by m square matrix. And it's also be symmetric, and also has this property from linear algebra called semi-definite. And this has really interesting consequences. Oh, one more thing, just in case that, just as a reminder, the diagonal of my m square covariance matrix is in fact the variance of every single measurement by itself, right? Because that's what every measurement column times itself is. That becomes the actual variance in every single measurement. And all the off-diagonal terms are the covariances, the pairwise covariances between every measurement and every other measurement. What I'm going to do now is our second favorite trick, or maybe this is the first favorite trick in linear algebra, is that if I have a square matrix here that describes the similarity in my data set, I'm going to reduce it by trying to figure out what are the chief, most important parts of this covariance matrix. And I'm going to do that by taking the eigendecomposition of my covariance matrix. Okay? And if I do that, if I take the eigendecomposition of the square matrix here, because of all its special properties, I'm going to get a bunch of eigenvectors and eigenvalues, m of them, right, because it's the m by m matrix, and where these are the eigenvectors in kind of in a matrix way. So this is the first eigenvector, second eigenvector, and so on and so forth, so that it becomes m by m, and my eigenvalues, the corresponding eigenvalues. Okay, every eigenvector comes with an eigenvalue. Here, all the eigenvalues are going to be non-negative because of the properties of my covariance matrix. So I can now rewrite my data set using my eigenvectors and eigenvalues in the following way. I can say that T equals X times W. This is my W matrix over here, my eigenvectors over here, right? So my X is my data set, so it's m by m like normal. W is m by m square matrix of all of my eigenvectors. And this thing here is going to end up being an m by m vector as well. So in PCA speak, these are called scores, and these are called loadings. Okay? So like all good popular algorithms, this has been reinvented many, many times in different fields, and so I'm trying to do a little bit of translation here in terms of the matrix algebra formulation and singular value decomposition formulation, as well as the statistical language. People call these things scores, and those things are called loadings. Now, what you've noticed here is I actually haven't done anything, right? I have failed at my goal of reducing the dimensionality, because the thing is, if anything, slightly more complicated than it used to be. I haven't actually reduced anything. Now, what I can do now is, instead of keeping all of the eigenvectors and eigenvalues, I can take a look at my eigenvalues, okay? And I can say that, oh, they're not all the same size, okay? The ones that are the largest have the most contribution to my data set. They account for most of the variance of my data set. So I'm going to pick the top R, biggest eigenvalues. Because they are, in this context, basically most important defined as accounts for the most variance in the data. Okay? And R, of course, is the letter I did not pick randomly. R is for reduced, because we are doing dimensionality reduction. We can then rewrite this formula here as T sub R, which means that top R is equal to my data set times W sub R. Okay? Where here W sub R is the top R eigenvalues from that matrix over here. I'm just going to literally pick the columns of W, the eigenvectors, that correspond to the eigenvalues that ended up being the largest in this eigendecomposition. Okay? So R, for example, could be quite a bit smaller than my M. So if I wanted to plot this on a piece of paper, I might pick R equal to 2, so that I can end up with 2 dimensions. And because of the derivations, I point you to the excellent videos on the PCA and the SVD that are available as resources for you in this course. You are guaranteed, in the sense of maximizing covariance and variance explained, that if you picked the top R eigenvalues here, you're guaranteed to have the best possible representation of by picking the top R vectors. Did I say this wrong? This is eigenvectors, not eigenvalues. Okay. So top R eigenvectors here. Right. Okay. So then we end up with T being an M by R matrix, and this W being an M by R matrix. by R matrix, which could be quite a bit smaller than the original data set. Okay, so to summarize, what we've done here is that we've taken a potentially large data set that is high dimensional. So we can maybe plot it on some axes. I'm going to fail in my ability to plot these axes here, but let's just say that it has however many axes that it has because it actually lives in some much high dimensional space. And we are going to use some kind of linear transformation called PCA or the SVD. Okay, these are just acronyms. I'm going to turn that into a much reduced representation where we can now represent the data set as the top using the scores in the top R components that we've learned. Okay, so we've taken something higher dimensional and put it into something lower dimensional just by projecting it and squashing it. And projection here in linear algebra really does jive with your intuition of what projection means, like in a projection screen, in a movie screen, right? So it is the shadow that gets projected onto the board by shining the light in the direction that we learned by PCA and SVD. So we can shine a light on this high dimensional data set and project it and look at where the shadows have landed in the lower dimensional space. That is all that's happening here. No warping, right? The walls are all flat. We're just doing shining a light from some direction onto a flat wall. And what we have guaranteed here, because of, again, I point you to the videos where you review the properties of PCA and SVD, is that points that start out close together in the original space, in the Euclidean sense, are guaranteed to be relatively close together in the projected space as well. But points that are farther apart originally, let's say I have another point over here, those relative distances are going to be preserved. So wherever this orange point ends up in the projected space, okay, it's going to be also relatively far apart. So relative distances, local and more global, in the Euclidean sense, are guaranteed to be preserved when you apply this linear transformation using the PCA that we have learned. And that is actually a really wonderful property because this is one of the goals that we had in dimensionality reduction, because we wanted to be able to reduce the data in such a way that things that are closer together should end up closer together, and things that are farther apart should end up farther apart. So this is like basically the simplest possible linear way of accomplishing that goal. Now, to review here, what we've done is connected our notion of distance and similarity, in this case concretely with the notion of covariance that's computed in this matrix formula over here. And then we apply our favorite linear algebra trick of doing the eigendecomposition to figure out the most important ways to represent the data set using this notion of similarity as equivalent to covariance to learn a linear transformation, a projection of the data set so that we can preserve relative Euclidean distances. Okay, this works totally fine as long as Euclidean distances is an accurate way of describing how far apart how similar or how far apart my data points are. So what we're going to do next, the next video, is that we're going to start them very gently warping this data set. Okay, we're going to start going to places where this procedure is no longer the most suitable, the best procedure, because it's going to be unable to learn cases where my data is warped because it's living on a curved manifold as opposed to a perfectly flat subspace. That's what's coming up next.